We will continue with groundwater. Earlier on the second slide of the first lecture, I used the terms turbulent flow and laminar flow without explaining these terms. Darcy's law is limited to laminar flow situations, situations where water can macroscopically be regarded to flow in parallel layers with no disturbance between these layers. The opposite of laminar flow is turbulent flow for surface water. This is characterized by disturbances, eddies, and a chaotic flow pattern. At the end of lecture 3, part 1, which is an earlier recording, I once used the word volume flux for small q, where of course I should have named this the volume flux density or specific discharge. The attentive listener must have heard this. As a take-home message of the chapter 1 and 2 additional exercises and lecture 3, part 1, very often in hydrology we have variables that we express in millimeter per day or meter per day, a length unit per time, but we must then think of millimeter or meter as representing a volume of water. This is a picture that I showed you earlier on, the water table. A water table that can establish itself freely is by definition the level at which the pore water pressure in the ground equals the air pressure of the overlying air. On average, this air pressure is the standard atmospheric pressure of 1 atmosphere, or when expressed in hectopascal, 1013.25 hectopascal. Instead of using this a little bit awkward standard value as the average water pressure at a free air-water interface, such as this water table, but it also goes for the level of the ocean or the sea, it is common practice to define the water pressure at a free air-water interface as 0. Thus, the water pressure has a value that should be interpreted with the existing air pressure at the air-water interface as a reference. So a 0 water pressure means that water pressure equals the existing air pressure at the air-water interface. And this is what we commonly do in hydrology. We simply denote this water table as having a water pressure 0. When we go down into the saturated zone, we have positive water pressures, and when we move upward from the water table, we have negative water pressures. Hydrostatic equilibrium, hydrostatisch evenwicht. Here we have a cross-section of the subsurface. Unconfined groundwater is groundwater where the water table, indicated with this sign, can establish itself freely. It is therefore also called phreatic groundwater, phreatic meaning free. This figure shows us the hydraulic head, elevation head, pressure head for a number of piezometers with their screens at different depths. We have a no water flow situation because the hydraulic heads for all these piezometers are the same, and we call that hydrostatic equilibrium, hydrostatisch evenwicht. Note that the screen of the leftmost piezometer lies below the reference level and that the elevation head, Z1 or Z1, is therefore a negative number. Also note that the screen of the rightmost piezometer is located at the water table and that the pressure head thus equals 0 meter. This is also stated here in the accompanying equation. Below the water table, the pressure heads are positive. Above the water table in the unsaturated zone, the water pressures are negative. Note that under hydrostatic equilibrium conditions, hydrostatisch evenwicht, no water flow, the water table and the hydraulic heads measured in the piezometers have the same level, but this is only the case for hydrostatic equilibrium. Flow patterns beneath lakes. These pictures are taken from groundwater science. Groundwater flows from a higher hydraulic head to a lower hydraulic head. We have the landscape, for instance, here, and we have the water table. The water table is indicated with this triangle. Here we have a larger hydraulic head in the subsurface than in the lake level, and thus groundwater is discharging into the lake. Here we have the situation the other way around. The hydraulic head in the lake is larger than the hydraulic head in the subsurface, and the lake is discharging into the groundwater. Here we have a combination of the two. To the right, groundwater discharging into the lake, and to the left, the lake discharging into the groundwater. And here we have yet another combination. To the right, again, groundwater discharging in the lake, and to the left, the lake discharging in the groundwater. But here we have a local system with a local topographic high, and part of the water in this system is discharging into the lake. Let's introduce some of the hydrological terms, and I will use the pointer. An aquifer is a subsurface water storing layer with high water permeability. Permeability is defined for our purpose here in general terms as a measure of the availability of a porous material, soil, sediment, or rock, to transmit water. An unconfined groundwater has already been defined as groundwater where the water table can establish itself freely. It's also called phreatic groundwater. An aquifer with unconfined groundwater is called an unconfined aquifer. A confining layer is a subsurface layer with little or no water permeability. Confining layers that totally block groundwater flow, this one or that one, are impermeable layers or aquifuges. Confining layers with low water permeability are called semi-permeable layers, leaky confining layers, or aquitards. Groundwater captured between two impermeable layers is confined groundwater, and the aquifer is a confined aquifer. Groundwater captured between two confining layers, one or both of these being semi-permeable, for instance here, is called semi-confined groundwater, and the aquifer is a semi-confined aquifer or leaky aquifer. This figure is a cross-section showing different types of subsurface water storing and water confining layers. The large hydraulic head in the semi-confined or leaky aquifer is caused by a high water table to the left and by a high water pressure in the aquifer due to the weight of the overlying ground. The semi-confined aquifer is recharged from upslope, and its hydraulic head diminishes slightly from left to right. And this is due to the friction that the groundwater flow experiences. When the hydraulic head of a confined or semi-confined aquifer lies above the land surface, as shown here, the groundwater is called artesian, artesisch grondwater. Above the overlying aquitard, we observe unconfined groundwater, and to the far right we find groundwater above an impermeable layer that overlies an unsaturated zone. unconfined groundwater underlain by an unsaturated zone is called purged groundwater, tijdelijk freatisch grondwater, and the water table, the purged water table. Note that the hydraulic head is highest in the semi-confined aquifer, which means that there is seepage, groundwater flowing upwards from the confined aquifer through the aquitard that separates both aquifers. And then for the Dutch-speaking students, we have the following terminology for layers in the subsurface. An aquifer is een watervoerende laag. An unconfined aquifer or phreatic aquifer is een phreatisch watervoerende laag. A confined aquifer is een afgesloten watervoerende laag. A semi-confined aquifer or leaky aquifer is een gedeeltelijk afgesloten watervoerende laag. And then for the confining layers, de afsluitende lagen, an impermeable layer or aquifuge is een ondoorlatende laag. A semi-permeable layer or aquitard is een slecht doorlatende laag. And a leaky confining layer, also an aquitard, is een gedeeltelijk afsluitende laag. Het land van Maas en Waal, the Maas River, the Waal River. This figure shows a schematic cross-section of seepage into a polder. The polder is made up of a semi-permeable clay layer and is separated from the rivers by dikes. Below the clay layer is an aquifer, and below the aquifer is an impermeable layer. By pumping any excess water into the river, the water table in the polder, this level, is maintained just below the land surface. The aquifer below the polder is provided with water from the rivers as shown by these arrows. Groundwater in the aquifer is confined by an impermeable layer below, an aquifuge, and a semi-permeable layer above, an aquitard. The hydraulic head in the aquifer beneath the river equals the water level of the river and diminishes gradually to the center beneath the polder. This is due both to the friction that groundwater flow experiences and seepage through the upper semi-permeable layer into the polder. The hydraulic heads in the aquifer are measured in the two piezometers shown on the left. The geographical distribution of the hydraulic heads in the aquifer, the potentiometric surface as we call it, is presented in cross-section by the broken curve. Note that the hydraulic head in the aquifer is everywhere larger than the level of the water table in the polder. This is the level of the water in the polder. This causes groundwater to seep through the semi-permeable layer. Seepage is largest just behind the dikes, where the difference in hydraulic head between the aquifer and the polder's water table is largest, and it diminishes towards the center of the polder, where the difference in hydraulic head is smaller. Here we see the result of seepage behind a dike for one of the major Dutch rivers during high water. One of the largest evacuations in recent Dutch history took place in 1995. On January 31st, 1995, and in the days that followed, 250,000 people were forced to be evacuated for a period ranging from 5 days to 2 weeks from large parts of the Gelderland River area due to a dangerously high water level of the rivers. If the dikes would have collapsed, many places in the Betuwe, the Bommelerwaard and the Land van Maas en Waal would have been flooded up to approximately 5 meters. At least the first 2 floors of many houses would then have been flooded. The Dutch dikes are old. They stem from the Middle Ages. Due to this, they have a low porosity. Had they been new, they would surely have collapsed. As a countermeasure, by placing sandbags in this seepage area, you would increase the hydraulic head here. By this, the difference in river level and hydraulic head here would diminish, causing a lowering of the hydraulic gradient. Then take Darcy's law. This would mean a diminishment of the seepage flow. This figure shows different types of interstices in the subsurface. Porosity is the maximum volume fraction of water in the soil. For a well-sorted, rounded, porous sand, the porosity N is in the order of 0.4. For a poorly sorted, partly cemented sand with smaller grains in the interstices, the porosity N is in the order of 0.2. For clay, for very porous, loosely packed clay, porosity N is in the order of 0.7, and for slightly compacted porous clay, the porosity N is in the order of 0.5. Sand consists of grains, and the forces at work in the pore space are mainly the capillary forces. Clays have a laminated structure and negatively charged surfaces that attract cations, positively charged ions such as sodium plus and calcium 2 plus in the soil water. The cations are bound to the clay sheets by electrostatic forces, and as a consequence, the soil water that holds these cations is also bound to the clay. These electrostatic forces that hold the water in clays are much stronger than the capillary forces that hold the water in sand. This figure shows us the volume percentage of pores in the subsurface along the vertical axis, and the textural classes clay, silt and sand, so going from the smaller to the larger particles on the horizontal axis. The porosity for clay is larger than the porosity for sand, and you can also see that by these numbers. Part of the subsurface water is readily available for water flow, this blue curve, whilst another part is retained by surface tension forces as films around soil particles or in small capillary openings or by electrostatic forces. And that's given in this curve. Note that the summation of water not readily available for water flow and water readily available for water flow equals the porosity. Again, despite its higher porosity, because water is strongly bound to clay surfaces, as I explained earlier on, the volume fraction of water readily available for water flow in clayey sediments is much less than for sandy sediments. And this is also reflected in the hydraulic conductivity values. The saturated hydraulic conductivity, usually abbreviated to hydraulic conductivity, is a proportionality factor in Darcy's law, by which both the water and the material through which the water flows are taken into account. So typically, clay has a higher porosity than sand, but sand has a higher hydraulic conductivity than clay. The porosity is a dimensionless number. The hydraulic conductivity is expressed in meter per day. So please do not confuse these. Just a slight further explanation on Darcy's law. This figure is a schematic representation of Darcy's experiment. but now with groundwater flow directed from right to left, so in the other direction, x2 minus x1 is a negative number. The difference in hydraulic head is h2 minus h1 is also a negative number, and this means that the hydraulic gradient delta H divided by delta X is a positive number. K, the hydraulic conductivity, the area A perpendicular to the flow are positive numbers, and this means that the volume flux Q is assigned a negative sign. So we have a negative value for Q. In actual fact, that negative sign is a reflection of direction of the flow. This figure explains the concepts of both homogeneity and isotropy. In a homogeneous layer, the hydraulic conductivity is the same at every location. The length of these arrows gives you the value for K, so K in a Z direction and K in an X direction. And here, the values are the same as here. But also here, the values are the same as here. In an isotropic layer, the hydraulic conductivity K at each location is the same in all directions, or in other words, independent of direction. And that's what we see in these two cases. In every direction, X and Z, K has the same value. So this gives us four cases: a homogeneous isotropic aquifer, a homogeneous anisotropic aquifer. This is a heterogeneous and isotropic aquifer, and this is heterogeneous and anisotropic. The saturated hydraulic conductivity is an important property of the subsoil. Together with the hydraulic gradient, it determines the volume flux density or specific discharge in the subsoil by Darcy's law. There are many techniques to estimate the hydraulic conductivity of the subsoil. All these techniques have their advantages and disadvantages. In practice, regardless of the selected technique, it is hard to obtain a precise estimate of the saturated hydraulic conductivity. This picture shows you the principle of the constant head permeameter for measuring the saturated hydraulic conductivity in a laboratory setting. You have a core sample in a metal casing, which you have taken in the field. Typical dimensions are a length of the core sample of 5 centimeters and an area of the core sample with a diameter of 5 centimeters. So it's a 100 cubic centimeter core sample. You can establish L and you can establish the value for A. This side of the core sample has a hydraulic head H1, simply the level of the water here. And then let's take the bottom part of this apparatus as your reference level, and this is H1, and the water flowing out of the system has a hydraulic head of H2. So the hydraulic head difference, H2 minus H1, the hydraulic head to which the water flows minus the hydraulic head from which the water flow dispatches, H2 minus H1 is a negative number. These are all positive numbers. We have a minus sign here, so your volume flux here is a positive number, and that's correct because the water is flowing upwards. You can simply determine this volume flux by simply catching the water here, and then you can determine the volume per unit time. So you know all the variables, and you can simply figure out what your saturated hydraulic conductivity is by using Darcy's law. Here we have a constant head permeameter in the laboratory with a young PhD student, now Professor Mark Bierkens at our institute, standing next to it. As you can see, your measurements are not limited to one subsoil core sample, but you can insert many of these. You can determine the volume fluxes here, and then simply by applying Darcy's law, you can figure out what the saturated hydraulic conductivities for these subsoil core samples are. Another measuring technique, also involving the use of one or more core samples of the subsoil, but usually performed in the field or during field work, is the Kopecky field method. A bottle is filled with water and closed by a cork with two open tubes. The bottle is then turned upside down and water is fed onto the subsoil sample as shown in this figure. The short tube lets the air in, while the larger tube lets the water out. When the water above the subsoil core sample reaches the outlet level of the larger tube, the water flow from the bottle is temporarily halted. In this way, a constant water level above the subsoil core sample is created, with water infiltrating from this water layer into the subsoil core sample. After the subsoil core sample is water saturated, and as soon as the volume flux Q attains a constant value, the hydraulic conductivity of the subsoil sample can be determined again by application of Darcy's law. Note that the water flow through the subsoil sample is downward, and that Q, the volume flux, thus has to be assigned a negative sign. As outflow from the subsoil core sample is under existing air pressure, the pressure head at the water dispatching end of the subsoil sample equals 0 meter. If we take the bottom of the subsoil core sample as the reference level, the hydraulic head at this water dispatching bottom end of the subsoil sample thus equals an elevation head of 0 meter plus a pressure head of 0 meter, totaling 0 meter. On the water receiving upper side, the hydraulic head equals an elevation head of L plus a pressure head of P1 divided by rho G. Both L and P1 divided by rho G being positive numbers. The difference in hydraulic head thus equals 0 minus, in between brackets, L plus P1 divided by rho G, close the bracket. So 0 minus L minus P1 divided by rho G. The hydraulic gradient equals the difference in hydraulic head divided by the distance. The distance is 0 minus L. Insert all of this in Darcy's law and you will get this equation. Please note that because the water is flowing downwards, that your Q, your volume flux, is a negative number. And please do not learn this formula by heart, but make sure that you can derive this simply by rewriting Darcy's law as I just explained. And this is just to give you an impression of the Kopecky field method, again in our fieldwork area in the Hautes-Alpes in France. And this is yet another picture taken during that same fieldwork, also of the Kopecky field method. This figure shows the principle of aquifer thermal energy storage. The left part of the figure shows the summer situation where cold groundwater is pumped out of an aquifer to the left. The cold water is used for cooling a building using its air conditioning system via a heat exchanger. Note that the groundwater that is warmed up during the heat exchange process is returned to the aquifer. In winter, the operation is reversed. The right part of this figure shows the warm water which infiltrated during the summer now being pumped out. The warm water is used for heating the building using its central heating system via a heat exchanger. Note that the groundwater that has cooled during the heat exchange process is again returned to the aquifer, now for later use in the summer, and so on. Groundwater holds its temperature quite well. The thermal conductivity of aquifers is low, and groundwater flow is slow, as we have calculated, causing aquifer thermal energy storage to be an effective technique for both the cooling and heating of buildings, replacing part of the electricity demand in doing so, and thus also reducing possible burning of fossil fuels and CO2 emissions into the atmosphere. At Utrecht University, near the Weening-Mijnes building, we have an aquifer thermal energy storage project in use. The saturated hydraulic conductivity K, as used in Darcy's law, strongly depends on the groundwater's temperature. Therefore, calculations of the volume flux Q and the effective velocity of groundwater in aquifers used for thermal energy storage should always take this into account. Okay, we have come as far as section 3.7 of my book, and you can now make all the exercises up to exercise 3.7.5. Good luck.